Hey, welcome all to this data science tutorial. I am Karthik. I'll be taking you through all the fundamentals of data science, in particular the types of predictive algorithms, what do you mean by big data, and with the help of many examples and use cases, I would make sure in another 2 hours we will be explaining and going in detail of building use cases and solving problems using the methods and ideas that we have from data science. All right, so in a broad agenda for this session is to understand what data science is, the sort of job roles, particularly the data scientist job role. We'll understand what it requires to become one, right? And we'll also see how do you normally solve problem, right? How do you break down problems into smaller parts and then start to use the ideas from data science to get to a really good and robust solution. And in the last part of the session, we'll cover certain components in data science, particularly the big data world, where we'll discuss some of the tools which we use quite often for handling large volume of data. All right, so let's begin with why data science. Right, so from very early days on, while businesses were growing, there was an increased demand and necessity for building dashboards and reports around the key business metrics, right, or what we otherwise call the KPIs, key performance indexes. And most of the time when such a requirement was presented to an analyst or for a business analyst or to any leadership team, the idea was we have a lot of transactional data happening or being collected in our systems which concerns or which relates to our business. And on a daily basis, these data sets are stored in something that we call data warehouses, right, which are large volume of data. But what was not evident in those times was the size of the data and the velocity at which these transactional data was created was not so big in size, right? So it was comfortably fitting in the traditional RDBMS databases, the relational database management system. So the typical examples of the such database systems are Oracle, MySQL, or Microsoft SQL Server, and many more, and even IBM's DB2. And then people also created pipelines as well as systems which were able to leverage these data warehouses where a large volume of different data sets were stored, starting from the transactional data to all the other data generated by the various systems being used in the business. The data which comes from the CRM to data which stores your employees' details and so on. And with the business intelligence systems, the data stored in warehouses were very quickly getting transformed into intelligent reports, right? When we said business intelligence, we all meant or all we understood is a sort of insight which is coming from your traditional reports which are more in descriptive in nature. By simply having a KPI being defined for your business or a metric being defined for your business, tracking it over a period of time, right? And in that way, we were able to see what is the health of the business and take corrective actions if something is not right. And then these reports are very well structured and scheduled at a periodic manner to be sent to the leadership team or people who are controlling the business actions and the decisions, which is in its entirety a very well maintained pipeline. Having the availability of the structured data to having the capability to store this in a data warehouse and building business intelligence report as well, right? With this sort of pipeline, things were going smooth. No one was complaining. There were a lot of data being generated and people were able to produce reports intended for the use of business leaders and people who were taking the decisions. But then suddenly there was this enormous amount of data which were starting to flow, right? As the businesses were maturing, 5-year business went to become 6-year businesses, 10-year businesses, and 15-year businesses. The moment that happened, the complexity in the businesses obviously started to grow because of the various strategic decisions the business teams took, as well as the complexity in storing the large volume of data also started to increase. And with this complexity, the issues around the time it takes to retrieve the data, the time it takes to build the reports, and many more other challenges started to appear, right? And because the kind of customers the traditional businesses had were also now pretty diverse, right? And understanding the customers was actually a key to flourish, with the competition also increasing in size and in volume. So then came this tremendous growth of the structured as well as the unstructured data with the platforms typically like Twitter, Facebook, and LinkedIn's of the world, where people are generating content and that content has certain behavior of the customers as well. And then came the new world of storing an enormous amount of data in a distributed fashion, and at the same time being able to process such large amount of data with the technologies like Hadoop. And then the data science algorithms particularly replaced what we were used to, like the traditional descriptive analytics based BI reports, to a more advanced and sophisticated predictive analytics based reports and insights, right? Which is not only able to see the historical data and give you some trends, but it is also capable of showing something for the future. What is going to be our course of action to make sure the business is going to run very well in another week's time or another 6 months or 1 year's time. And that led to a great surge on the scientific discoveries, which in a way even started causing a disruptive sort of trend in the industries. The industries which were nowhere first thought of, like could survive, are now flourishing, right? The examples typically comes from the Uber business model or the Airbnb's business model and many more. And these companies typically have enormous amount of data being collected, right, from their application. So with this new paradigm of data science, a lot of technologies and the ideas which were traditionally very separate were then started to emerge and were put into one big umbrella, right? And in terms of the data, there was a multi-fold increase. In terms of the technology, many technologies started to come on to deal with this data search. And at the same time, the descriptive world started to change into a predictive world, and the algorithms started to become a bit more complex. So in the coming slides, I'm going to talk about in detail how is this paradigm change really happening, right? And in which ways it is contributing to the development and to the successful operation of a particular business model as well. Right? And with the data science becoming a field, many of the other domains where people were initially saying that we don't have much data to do the analysis, or we don't have much data to validate our hypothesis and so on, are now thinking in a way that even if we don't have data, can we start collecting it, right? So this is the kind of mentality shift which is happening with the advent and the ease with which many tools are helping people build data science solutions. So we'll go in some details of how people do data science and what really data science is as a subject, right? So all of these things you might be already knowing, but one fundamental difference that data science is bringing to this world of business and cutting edge data driven research is to say that the subject as a domain is actually bringing in a lot of different concepts and subjects areas together, particularly the programming expertise of a person, the ideas around statistics and machine learning kind of concepts, and a large amount of emphasis is also given on identifying the domain knowledge, right? For any successful implementation of a data science solution needs that you understand the problem statement well, and particularly the business to which that problem statement belongs to. So if I am solving a problem for e-commerce industry, I need to understand in and out around the problem that I'm going to solve. So for instance, if Amazon has come out with a recommender system, right, which suggests similar looking or similar look-alike kind of products when some customer is actually on a product page, the algorithm has a purpose. Obviously, it is a very well designed algorithm for you to explore and discover products, which otherwise in a virtual sort of a business setting where you are seeing products in website rather than physically feeling the touch and the quality of the product in a superstore, the ideas needs to be completely different there, right? And that needs to be driven with certain business metrics also in mind. So if traditionally before the recommendation algorithms really came in, if people were using or saying that my business gets a 1.5% of conversion, which means from the number of people who are visiting my website, how many of those are actually buying the product. So if that conversion rate is 1.5 today, after implementing this data science solution in the form of a recommender system, that number or that rate is going to go from 1.5 to 1.8. Right? So there is a strong motivation around solving such kind of problems for the use cases, which is very business specific. So that's where this third element really comes in. With the knowledge of programming and stats, you also have a person who can guide you to identifying the right problem statement, which is the key, right? So there is also a lot of hype in industry around this role called the data scientist, right? And a lot of people believe that I have a data scientist in me, but maybe I need to dig through what expertise do I have to become a data scientist. There are enormous amount of articles and studies as well as industry job portal definitions which describes what data scientist means. With that, most of those materials are true in its sense, with typical such kind of Venn diagrams, which is again available in many forms. In essence, if a person is like very good in the foundations of the mathematical ideas like stats, discrete mathematics, information theory, combinatorics, and a lot more emphasis is actually given on the machine learning expertise as well, right? But only knowing mathematics is actually not enough for a data scientist. There is also skills demanded of you to have the understanding of basic computer science, right? Which involves data structures, algorithms, and programming skills as well, right? And with that sort of understanding of computer science world, you are also sometimes expected to have the ideas around system designs, right? Which we normally call architecture, infrastructure architectures. How do you design a distributed system, and how do you run a program or algorithm which is working on distributed data sets? Right, so there are many ideas on building an algorithm, keeping in mind the designs which are made only for distributed systems. So that skill set is like one of the pillars to be in this role. And one more very important and sometimes the most neglected skill set among data scientists is to have a very keen understanding of the business for which they are working. Right? Whether it is domains like economics, finance, or in general business development, you need to be very aware of if you are building a machine learning model or if you are building a data science solution for a use case, how does that use case impacts the particular industry for which you are building it? Whether it is for some social cause, whether it is for some business, or whether it is for maybe some fun hobby type, right? So every use case has sort of impact. And that impact needs to be known and needs to be thought through well for you to be able to come out with the right solution. Otherwise, there are hundreds of machine learning algorithms, hundreds of programming languages, and many can actually go and read about it and be very good in mathematics and as well as the computer science domain. But what comes a bit with experience is the business knowledge, right? Or in other words, what we call the domain understanding. So that's why typically in a data science team, along with a data scientist, people also have the domain experts who have the complete understanding of the business processes and who've been working with that business for a very, very long time as such, right? But in short, if I would like to summarize, with a very good understanding of mathematics, with the skills to have a depth of the understanding in computer science ideas like algorithms, data structures, and programming, if you gain the business domain understanding as well, you as a person has this 360-degree view of looking at a problem and coming out with a really good data science solution, and which is a very sought out skill in the industry nowadays and very rare to find. People typically like reach a PhD level and then get into such a role in big industries. Obviously, there are a lot of exploitation as well for the designation, but like keeping those discussion apart, like this is what is actually required for becoming a data scientist. Right, so typically these are the sort of responsibilities. You need to have a very in-depth view of everything. Nothing can be like put in very simple terms. You go deeper, understand the various features concerning the use cases. You need to understand, build, and even after building, optimize the sort of models you are building for the use case, right? And the understanding of all the different algorithms, all the different machine learning or data mining or the artificial intelligence algorithms, and the ability to map that to a given problem statement. That's like the key for you to be successful in coming out with a really good solution, right? And also when you are working for a company, it is important that you are able to think through the various sources of information, not only the data which is available with your organization, but how do you like normally augment the data which is in-house to the data which you bring from outside, right? So there is again a large amount of effort and analysis goes on those places where we think of how to get more information. And then comes also an important step in building any model or doing any analysis is to build pipelines which can process, clean, and verify the integrity of the data, right? And this is the key step, because any kind of insights drawn from untidy data which has a lot of issues around the processing or as well as the integrity, the insights are not going to be right. At the same time, if you're depending on such kind of models for building a production grade algorithm, which can be like can be like facing the customer, things are not going to be very good, right? So again, this process is like very important. And as I said, understanding of all machine learning algorithms is actually a key to succeed with the solution, right? So with this understanding of what data science is about, what role a data scientist plays, let's also understand a bit of detail around how to create a problem, right? And how do we break the problem into smaller part, which can then be like solved using all that techniques we have from the world of data science. So that is again the key to make any model succeed through the implementation phase and then finally getting into production. Because if a problem is wrongly chosen or if a problem is not so relevant to the business, it might happen so that the end result of your data science model building exercise might end up in a failure because the business was not aligned to the problem that you are solving, or the problem itself was not so relevant for the use case you have chosen. Or it could also happen that the problem you have chosen is so broad that coming out with the solution is not so feasible so quickly. So having a right problem to solve is the key, and being able to iterate through the processes if the problem is not right and come back like a feedback loop is also like a important step in this process. But it obviously starts with the discovery phase, where you answer questions like, is this problem relevant to my business? Is this problem at the first place solvable, right? Or is this problem precise enough for me to like handle it in a nice way? If you have answered that, then you start the process of looking out, where do I find the data to solve this problem? You explore all the sources in hand first, like in your organization, and then look out for the outer third-party data sets as well. Maybe typically of the data sets collected by companies like Nielsen, where they do a lot of market research, or data sets collected by companies like PwC or Gartner, who also like do many such kind of market research. So there are plenty of resources going for such data set. And once you have successfully explored all those sources and collected the data in one repository, then comes the phase where you start your planning, right? Where you start your model planning. And in this phase, typically you do the kind of cleaning activity as well as verifying the integrity of the data sources. And if you do it well, chances are high that all the issues which exist with the data in terms of being unstructured, in terms of missing information and so on, will all be removed at this stage. And at the same time, you will also get the sort of some insights from what the data is trying to tell you. Soon after the model planning exercise is where you start to plug and play this data with all the sort of machine learning algorithms or all the sort of analytic approaches you have with you, right? And this model building exercise like goes on in a very iterative fashion, which simply means if some model is not giving you the best results, let's try another. And people do a lot of trial and error before finally saying this model is the best model and I can like use it to operationalize or put it into production, right? So once you put anything into production or like make it operationalize, you start to communicate the results which comes out of it, right? Because the model is now facing the production environment and their customers are coming in, you are collecting a lot of information around the customers and seeing what the results of this model kind of really showing. So for instance, if you can relate this to the same example that I took for Amazon's recommendation engine, if your recommendations product are very relevant, the chances are good people will navigate from a particular product page to the recommendations you are showing them. And that might also increase their chances of buying the product. But if nothing is happening around the business metric that you defined, which will actually decide the success of the algorithm, then you will conclude after discovering this recommendation, like after implementing this recommendation algorithm and putting it into production, nothing is actually moving, right? So the key to success would also be in the fact that we are able to communicate the results very well and keep a track of it, right? And then maybe over a period of time decide whether this model is really doing good or it's time for it to like go away. So there are some hard calls as well in the final stages of any model. Right. So maybe let's take some sort of more detail around this process flow that we just went through, like starting from the discovery to the communication of the results. So as we could know, as we kind of see in every business scenario, the data that we are collecting at large is not only coming from one source of data, which is very well structured, but there are like different platforms and different systems inside your business, which also generates a lot of data there, right? So for instance, if you are running your website, the website needs to be supported from an army or like a large pool of web servers, and each web servers do a lot of logging, right? So if Amazon is hosting their website and in the payments page, there are a lot of errors while the order is being processed. All of those errors will be returned to some log, right? And if you have built a data pipeline which can on a continuous basis read these log files and report or extract the informations around failure, then it is easy for you to understand that something is not right when the customer goes from the product discovery phase to product purchase pages. Right? Somewhere the payment interface is broken or somewhere navigation is broken, that is resulting in the order failure. But that kind of information is not so easy to know when you're like running a business of scale like Amazon. So you need to build this system automatically of collecting the log files and able to extract such information. So is the case with customer insights as well. Many of your customers are logging through social media platforms like LinkedIn, Facebook, or Twitter in many of your websites where you are running some business. So luckily for businesses, with the social data coming in, the social platform data coming in, the customer insights are many in number nowadays. So many people have built like 360-degree suits to understand their customer behaviors in very nitty-gritty details, right? Starting from an insurance firm to companies like Amazon. So with this data coming in, the challenges are even more because the data is no more in structured format as it used to be in the case of a transactional data, like the order purchase information. In this case, everything is in text. So we need to come out with methodologies which can help us deal with such data, right? And many more to discuss. Census data, data streamed via online services like coming from Twitter, because Twitter has a large volume of data flowing in continuously. So if you want to build any sentiments around, let's say, how your brand is doing, what customers are talking about your brand and so on, there are like many such use cases. You need to make sure that such kind of information is continuously being pumped into your systems through some sort of APIs, which platforms like Twitter offers or platforms like LinkedIn or Facebook offers. But there is obviously some limitations in what kind of data you can get and what kind of data you cannot. So in short, the types and the structure of data is growing quite complex. With that comes the challenges of handling that. At the same time, handling that at scale is also quite a difficult thing to do. But the good news is there are a lot of technologies which are helping us how to do that. So I'm going to discuss that in coming few slides. Right. So with that discovery comes the challenge around the data preparation. As you could see, the data is not so good looking here. Everything is separated by a semicolon, and we have a lot of attributes given in any given data set. Right, so here if I take a use case around a doctor getting the medical history of a patient, particularly the informations like if the patient is a female, how many number of times she got pregnant, information like the plasma glucose concentration or the blood pressure information and so on, right? And the purpose might be from a simple profiling of the patient to as complex as detecting a onset of a particular disease like diabetes or cancer and so on, right? So with a lot of ideas around the data set that comes from such a use case, the emphasis is actually growing more in terms of making sure that you are coming out with standardized processes to handle such kind of varied set of information. So here the problems might come from the data consistencies to the incorrect data formats to values which are not at all relevant, right? So in order for you to handle that, you need to give a glance at the data set and build maybe some sort of basic methodologies to do and identify such issues. The moment you are able to do that, you can very easily take those data points either out of your analysis or come out with methods which can keep the data in but handle it separately, right? So the data preparation is actually a key step for you to get to a like really good value or really good model in the end. So anomalies like this, right? For example, here if I take the blood pressure, there is this data in the third row which has like a very high value. So 6600 for a value of blood pressure is something which is not possible at all, right? Something similar will happen with like inconsistencies in the data format. For instance, when the number of times a woman getting pregnant attribute is like storing data in an integer form, and suddenly you see a character there, right? Which is actually telling, though the information is right, but the way it is being put in this data set is not, all right? So when you build the model or build any analytical things on top of this data set, things might not work out very well there. It might come out with certain errors and so on. Right, so the step here is very self-explanatory. There are many missing values also in the data set sometimes. So all of these things has to be handled, and then you go into the next level of saying, now how can I like build a really good plan to build the model and so on. So to do that, we are going to use the standard methods like the exploratory analysis using the tools like SQL, R, or SAS. There are plenty of such tools nowadays which can help us to identify such issues and then take a corrective action on it, right? And this will also help us with the exploratory analysis. It will also help us to see which kind of models we can use to build our solution, right? So with this planning, a lot of ideas are obtained. As you could see, the distribution of the data is very well coming out. With that distribution, it gives us certain information around how and in which way the data is really kind of distributed in the given data set of ours, and then accordingly get a really good sense of what sort of models will fit this data, right? So the wordings are like very clear here. How do I make a model which will suit the sort of distributions or sort of summary statistics that I see with the given data set? And with that understanding, we have then once again all these tools available for us to build the models very quickly. So once we understand the problem, discover the problem in the very crisp terms, prepare the data with all that cleaning approaches being taken up, like handling missing values, handling inconsistencies in the data format, and so on, we are very well in a position to fit this particular given data set on many modeling techniques. And in this modeling technique, you can see that the problem because is very clearly defined, whether it is a problem of classification, whether it is a problem of clustering, and so on. We know that which models will be very suitable for it. And because we have all these tools available with us, building the model is also fairly simple process, given you have taken sufficient amount of effort in the preparation stage. Right, but in the end of it, things might look like this, right? So this is a typical decision tree in which all the attributes of your data set are being used. So if I like go from the top and read in any one flow or any one particular branch of this tree, patients with glucose level less than equal to 127 and patients who are pregnant for less than 5 times and age being less than equal to 28 and the BMI being less than equal to 30.9, the chances of that patient getting diagnosed or being predicted for the onset of diabetes is negative, right? Similar is the case with any other route that you choose in this decision tree. So such models are quite intuitive, at the same time quite powerful to do things using the historical data and predicting for the future. It's quite a powerful insight if you know that for a patient you are able to predict the onset of a particular disease well ahead of time. Imagine the kind of cure and kind of diagnosis that you can plan. Okay, so with that, you are ready to build this sort of code and the model that you have done or created into a production environment, right? As I said, these reports can then be in real time give these model outputs, and often is the case that the model runs offline, right? And the model is then prepared in a way which can then handle a data which is not seen before. So for instance, if I talk about the Amazon's recommendation algorithm, they train on a large amount of data to build that model. and those models are then kept offline, right? And when some new products are now discovered or now uploaded by the various sellers around the world, this model will start to work on this new data set based on the information that the model is extracting, right? So in this way, a model which is built offline is actually working in the real-time production environment. Obviously, behind the scene, there is large amount of computation power involved, and at the same time, a very well-designed architecture of these systems as well. And you should also be noticing when the model is actually in the production environment, if is there any sort of delays or performance issues, because these models are quite complex in nature. It might happen so that the output or the decision making part of the model is actually taking time in real time. So you need to fine tune then based on that and see if there can be something done about it, right? And in the end, if everything goes well, the stakeholders are going to be quite happy, and we will be able to come out with a clear communication saying the model is best to this extent, and we are planning to even make this better in the coming days. But it is very important, once the model is deployed for some time or for a prolonged number of days, you should be able to see through the results and understand if the model is really good or not. If not, what can we do to make this good, right? Typically a rule set will look like this if you are building a decision tree. All right. So often in the process of trial and error, you have the data set ready after the data preparation, and then you decide to use, let's say, a decision tree algorithm, right? So that you start by doing that. But then comes the moment where you say decision tree might not be the best one for this, right? Maybe some other algorithm. So it is important that when you are framing your problem, you should be also considering the fact, is this problem more suited for a decision tree model or more suited for a clustering sort of model, right? So what is the difference? The difference really is in the way you ask the problem. For example, if I'm trying to build a particular model which will predict the onset of diabetes in a given patient based on the previous medical history. So the question I am asking is whether this patient is going to whether I am kind of going to predict the onset of the diabetes on this patient or not, like whether this patient is going to get diabetes or not. The answer is like quite binary here, yes or no, right? So the classification problem that we are talking about here is to put the patient in any one of these categories, the positive result or the negative result. And things like anomalies, right? When some let's assume you have a system where you are getting to see a lot of incoming traffic, which might be your website that you are hosting, and many people are coming and buying something. And then sometimes there are these evil elements over the web, over the internet, who like make your life a bit more difficult, right? Because they in a way influence a normal traffic and then comes like bombarding with sort of what we call in the security domain attacks, right? So when a normal flow of traffic is happening in your or being witnessed in your network, and suddenly some abnormality starts to show up, right? Either in your order processing system or in your stream of input visitors system or many other possible systems. So if something is detected being weird, you should be like raising an alarm very quickly, right? And typically these kind of approaches follows a sort of a time series model. When you know typically in a peak hour of your business, you will never get a volume of, let's say, more than 100,000 visitors. But suddenly one day in a non-peak hour, you see a volume going to 10 million visitors. That's not something which is known from the historical data. So there is some sort of abnormality there, right? So there are many ways of detecting such anomalies and then raising certain red alerts. And you can obviously ask questions like how much or how many kind, right? For instance, if I am trying to understand or predict the value of a property in my vicinity, there are hundreds of factors which will determine the value of a given property based on where I am living or where I am looking for that property. Things like the crime rate of that location or distance of educational institution nearby the property or good shopping places and so on, right? Based on that, if you are able to design a model which can in very crisp terms predict the value of the property rather than saying whether the property is worth buying or not. So there is this subtle difference between modeling a problem as a classification problem, which is about saying the data sets or these sort of patients belong to a category A to category B, versus saying predicting the exact value of a house or a property, right? So the problem kind of translates now to a different dimension. So is the case with problems like clustering, which doesn't do both ways of doing classification or regression types. It says, can I group the data into similar buckets? And by that, can I know some properties which are very similar for this group of data versus another group of data, right? So once again, the problem changes, the way I am approaching the problem also will change, and obviously the machine learning algorithm that I'm going to use to solve that problem also changes. So where you can like find such sort of application, typically where in cases like identifying customer behaviors, right? When you are designing some email campaigns to be sent out to all your customers with a very particular message in it, saying you are getting a 10% offer, and this 10% offer is for a product category, let's say in fashion, versus a product category, let's say in electronics. So if I have the understanding that there is a customer segment or there is a customer group who is very keen in looking out for fashion category of products, so my campaign emails, the emails which I'm going to go send and target the customer, can very specifically designed to offer fashion products, right? Or to send kind of a catalog of fashion products which are newly released or which are like having some sort of discounted offer there, right? And with all these sort of different problems, we can also like visualize something like, if the algorithms are trained offline and then only put in the production environment to handle the new data sets rather than being trained in real time, there can then also be a requirement saying, can the training process also happen online, right? There is a typical difference here. So when you are building a classification algorithm or a clustering algorithm, or for that matter regression algorithm, you have actually seen the past data and trained your model offline, and then you are putting only the end result to be faced in the production environment. So in a way you are not training on real-time basis. But what if you take examples like driverless car, like the autonomous cars which are able to navigate through a city lanes by assessing the risk of the obstructions in the front, the traffic signals which are coming in, people who are behind you and on the left and right side of you, right? All of these situations has to be analyzed in real time. You cannot say that I'm going to wait in the middle of the traffic and my server will build the model for some 5 minutes and then I'll give you the results. That's not possible. So in reinforcement kind of learning approaches, the idea is in real time, looking at the environment around me, can I take a very quick decision and give my results back to the control system who is actually navigating the path of the car there, right? So obviously this system is quite sophisticated in its design and also difficult to build in there. So in essence, if I talk about the type of learnings based on the type of problems that I'm trying to solve, we can like easily categorize things into supervised reinforcement and the unsupervised learning methods. Wherein in a supervised learning approach, we are saying that there are a lot of input data available for the problem or the data set that we have created for the problem or collected for the problem. Along with that, there is a sort of an label or a teacher who is telling us that the data point number 1 or data row number 1 is having a particular meaning associated it is. For the same example that we took for predicting the onset of diabetes in a particular patient, we can say if we have a data set which in each row has a last column saying, based on the historical data and the expertise of a doctor, can I like label this patient into a patient who got diagnosed with diabetes or not, right? So if there is somebody who can help me to get this initial data set ready, so my model can go and learn these teachings, which in simple terms means, given this input data, somebody has told me that this patient is having diabetes, then I can very easily build a model which can look out for the patterns in the input attributes like the BMI, age, and the blood glucose level and so on, and come out with a final result which says, based on this, I can see a pattern that the values in this range will give a particular patient the sort of onset of diabetes there. So having a presence of such a variable, such an attribute in my given data set largely helps to build a model for what we call in a supervised learning, right? But if you say that there is no such variable with me, I don't have an expert doctor, I don't have an expert teacher who can tell me that this data row means something. So in that case, I'm like clueless. How do I go and train myself? So all that I can do in these kind of situations, and typically this is what happens in the case of a customer segmentation model, right? You don't really know about your customers very well. These are behavioral traits that you are trying to identify. And very precisely or crisply, you won't be able to tell that the customer is going to definitely buy an item if you know that he or she has purchased something in fashion. It's your understanding of the various data points from the customer, but the max we can do is to create a cluster or a group of similar looking customers. But that doesn't say that the customer is actually 100% fashionista kind of a person who will definitely, no matter what offer you tell or no matter what offer you give in the email, is going to buy the product. That kind of certainty is not possible, right? So there is no teacher who can tell you that the person XYZ is 100% sure win if you send anything related to a fashion category. In human being, this kind of traits is like very difficult to come out with. So in such cases, the unsupervised learning methods really work well, right? And then comes the reinforcement learning. As I said, in the examples of driverless car, such kind of learning algorithms are quite popular. And the idea behind all these reinforcement learning approaches is when you kind of say that if you do anything wrong, I'm going to penalize you. But if you like taking the right actions in the given environment of yours, I'm going to reward you in the moment in that particular situation. And this sort of feedback based action and the reward kind of works very well with the model learning to do the right thing by the means of rewarding it. And if it is doing something bad, you also penalize it, right? It's like teaching your kid to do good and bad things with the right sort of action. For good, you reward, and for the bad, you penalize. Right. So with the ideas around building a process flow for coming out with a solution, given there is a very crisp problem, we also now need the help of technology to do so. Somebody's ability to do these kind of analysis or build a model is actually limited in large number or in large essence to the capabilities you have, right? As a computer science guy, you will be able to write good code. As a mathematician, you will be able to prove theorems or write things as a model, right? But to combine these ideas together and being able to very quickly develop programs based on the mathematical ideas is like a very difficult skill set to have, and it's time consuming as well, even if you are able to do so. And that's where the programming languages or things like the programming languages or what you call like tool as well, like R programming really comes to the rescue. So as many of the industry folks have already started using the R programming language as one of the best tools for doing statistical analysis, on top of it being able to also build machine learning models, and in a very quick manner, right? It also provides you frameworks and methods which can identify problems in the data, right? And all you need to do is, once you have done with the sort of analysis in one complete flow, you can repeat it for any other data set as well, right? By creating a sort of a program. So R is quite powerful in its nature. Initially developed only for statistical computing, but later on it emerged as full stack product which offers the end-to-end support for starting from the data cleaning or data preparation and till the model building exercises. And people build prototypes around their problem definitions very quickly, given everything is in place and you know how to define and use all the different modeling techniques on the given data set. Right. And on top of it, not only programming and statistical help that R can do, it can also do a really good aesthetically well-designed data visualizations. Oftentimes when we do analytics on any given data set, whether it is descriptive or predictive, we come to know that in most of these places, anomalies or the issues sometimes are not easy to capture if you look at the raw data, right? But the moment you put the raw data in form of a visual, thing starts to emerge like very clearly in front of you, right? Sometimes statistics fails in terms of saying that there is certain differences between any two data sets, but the moment you put that into a visual form, pattern starts to emerge. So to read more about it, if you would like to go and see one of the classical data sets, which is called the 𝐂𝐝𝐻-𝐶𝐚, one of the very quite famous data set which proves that, so it is actually a collection of 4 data sets with 2 attributes each. And the 𝐂𝐝 data set shows us, even though in all the 4 data sets, the properties like mean, standard deviation, correlation, and even the regression line being exactly the same, when you put that in a very simple scatter plot of the X and Y attribute, the 2 attributes that is present in all the 4 data sets, there are like quite a number of distinct differences, which was initially not captured by just looking at a pure stats like standard deviation, mean, or even the correlation values, right? So that's how powerful data visualization is. And with the tool like R and the packages like ggplot kind of packages, you are able to create very good looking data visualizations. And the good thing is it is completely open source. So compared to software systems like SAS, SPSS, which is being charged at a very per user or per instance kind of basis, R is completely open source. So anybody can use it without any commercial liabilities there. And also if you would like to change certain aspects of the code, you can like freely do so. Okay, so some basic terminologies and ideas about how to look at in a data set and what sort of information a data set provides you, right? A typical structured data set will maybe fit in a CSV format or an Excel kind of a format where there are like many rows and many columns. Each column is a particular attribute telling us certain information. So if I go back again to the diabetes example, if I have the records of 1,000 patients with me and all the attributes or the various tests that the patient went through, so each column there has a different sort of interesting information to tell us, right? In a very structured world, things are like quite easy to look at. But now imagine that you are going to deal with a data set which is quite big. For instance, instead of saying 1,000 patients, I am now going to tell you 10 million patients, right? Or 1 billion patients, maybe a hospital chain which is doing some sort of collection of data across the world. So in those cases, maybe organizations like WHO, which does that in large scale, working with many countries. So in there, if you see, the data is not only large, its variety is also like many, like as I mentioned in the beginning. The data is in form of structured way like rows and columns, or it can also be in a way where it is completely unstructured, like in textual form, right? So the world of big data particularly handled this challenge along with some more benefits as well. So the technology you hear in the world of big data like Hadoop, Spark, and many more like tries to basically handle this famous 5 V's. People sometimes argue that it's only the 3 V's, not the other 2, but to have kind of complete coverage of what exists or what is being talked about in the big data world, these are the typical 5 V's that you hear, right? Starting from the volume, as it is like very easily understandable, large amount of data, with the variety coming in, where you have various sort of data sets, starting from a simple looking CSV file to a very complicated video file as well, right? Where the extraction of feature and processing the video itself is a big task. And then comes the challenge of velocity as well. Things like dealing with Twitter stream, right? So if you are building any analytics on your customers or on your brand based on the data that is coming from Twitter, so if you have built this API pipeline between your data repository and what Twitter offers you, you have to continuously deal with the stream of data which is flowing inside your systems. And in order for you to be able to do that, you need technology, right? You need this big data technology to be in place. And how to do or handle things like processing things and putting things in queues and being able to efficiently handle situations like deadlock and all that, right? And then comes also the things like finding the correct meaning, which is like seeing the value from the large amount of data and being able to spot the uncertainties and the inconsistencies as well in the data, right? So with this big data world, all these 5 V's are in a way or the other is like very well handled, which in the traditional database management systems was actually lacking. So the traditional RDBMS world, the traditional relational database management system world of the Oracles, of Microsoft SQL servers, of the IBM's DB2, all of it like gave away the moment the variety of the data started to change, right? So in traditional RDBMS system, there is literally no way to store videos, right? Imagine how you store a video in a table. Like, it's very difficult to imagine. Maybe you can process the image, get certain informations of the image in a matrix format, and then maybe create a table. But it's very hard for you to like literally put the image file in a RDBMS table. Like, there is no schema which can support that. But in the world of big data, that's quite possible, right? So there are many more benefits as well of such a system. And typically the first of its kind wherein such kind of things were leveraged is the technology called the Hadoop, Apache Hadoop, initially invented in Yahoo, and very quickly its adoption was taken up by many other companies like Google, which contributed heavily to flourish this technology, where people designed ways to store the data in a distributed form and then come out with algorithms or techniques to process the data, right? So if you say that I can offer you a distributed system to store large volume of data, but I don't know how to process it, then the system is kind of a failure, right? So when Hadoop was designed, both these things were kept in mind. The framework offered a very good way of distributing the data and at the same time being able to efficiently process the data at scale and in parallel. So imagine Google, which kind of crawls every single web page in the World Wide Web on a daily basis. For it to be able to give you the search results in a fraction of seconds time, it need a large army of systems working together, right? And this large army of systems are distributed in nature, and your queries are actually quite fast because of the reason that the data is retrieved quite quickly, because you have this parallel and distributed architecture built inside the Google data centers. And in essence, if you look at, as I said, there is always this two ways of doing an offline and an online processing. So as you all might be knowing, Google has this PageRank algorithm, which is actually pre-computed. The moment you crawl a particular website, and you can like test this as well, if you create your own new website, for some days Google kind of somehow don't show your web page for the queries you might have. Fundamentally, there can be two reasons. Your page rank of your web page is not so high and you are not able to find your web page, but it might also be the case that because you have created something very unique which is not actually present in many other sources of the web pages or many other web pages. But even then, if you have a unique content which is not there in any other website, the Google is not actually showing the results in the top. And the very reason for that is Google is still taking some time to crawl and get the content of your website. So in 1 or 2 days, you will start to see that the Google search is actually picked up your website and it is now showing. So all of these operations at one point is actually happening in offline mode, right? And even including the page rank calculation. So these web pages with the URLs and the page rank values are stored in some structured and kind of in a structured way in some sort of repository. Then comes the other application part, which is actually the Google search engine, which simply hits these structured information and see what is the page rank, and maybe a simple process of sorting the result in the descending order of your page rank, showing the top page ranked web page in the first, right? So this world of distributed and parallel processing is actually quite diverse, and there are like so many use cases which companies across the globe have explored, right? So whatever is the capability or the sort of strength one particular technology provides, there is actually soon a replacement coming, right? That's how fast the software industry normally moves. So in the early days of Hadoop, and even in the latest version of Hadoop, it happened so that there are certain processes which is quite tedious because of the two reasons: the enormous amount of data, right, on which you have to process, and also because of the complexity of your process, right? So because of these two things, it takes a lot of time for anything to be done in a distributed and a parallel environment like Hadoop. And with the storage mechanism that you have when things are actually stored on your disk. So what happens in a typical data center, you have many hard drives, or what you call the SAN disks, which has a predetermined or a particular defined IOs, the rate of input and output, right? So if you measure for a typical SAN disk, you will get a value from the manufacturer or from your own experiences what is the rate of input and outputs, which simply means how much time does it take to retrieve a data point from SanDisk and to write a data point to a disk. And typically it is true for your own machine as well. If you go and look out for in your C drives and C drives, you will see that there is some level of latency to retrieve and write something back to the disk. Whereas if you take RAM, right, which is your kind of an volatile memory where things are stored temporarily and it is like vanished the moment you turn off your machine, right? And many softwares have leveraged the random access memory, which is your RAM, for the fact that IOs in a RAM is much faster, right? So fundamentally, when Spark came in existence, Spark said, why can't we use RAM to completely store the information as well as process it, right? And there comes the time when majority of the processes which used to take a lot of time in Hadoop, Spark showed that by keeping the data in RAM and processing it on top of it, the processing speed is, in some benchmarking studies, is at least 100x faster, right? And this 100x faster time is actually achieved because of the RAM as a fundamental storage unit. And the second was the design in the process, the change in the design of the processing there. Which was then later, like in Spark, everything which is being executed follows something called directed acyclic graph. All the processes are actually represented as a DAG graph, and then the processes happen. So even if you don't use Spark with a RAM-based storage facility, but rather a SanDisk-based storage facility, the speed is actually 10x faster. So this was like the Eureka moment for the industry folks who were in their traditional Hadoop job schedule used to wait for a day or maybe 10 hours or 5 hours to come out with results. But with Spark coming in, things actually improved 10x or 100x times, which was actually enough motivation for people to migrate quickly to Spark from Hadoop. But the fundamental architecture around the distributed and the parallel sort of systems kind of still remained. And one another beautiful thing that Spark did is to provide interfaces to many programming language. So with Hadoop, people were pretty restrained to using only Java as a programming language, right? Though it provided the supports later on, but in the initial days of it, only Java was the language in which people used to write programs to be executed in a Hadoop cluster. But with Spark coming up, they opened a plethora of such interfaces with R, with Python, with Java, with a programming language like called Scala, which is actually the native of Spark. And with all these benefits, there was like enormous amount of effort industry people started to put to bring in the Spark cluster and slowly transitioning from Hadoop to Spark. But the transition is like happening slowly. It is not completely that one fine day Hadoop will be gone and Spark will take over. So it is happening, but not at very fast speed, right? And the good thing is, because Spark provides this interface to R as well, though Hadoop has also one such interface, we are now in a situation where we can leverage the capabilities of R, which is in its support for statistical analysis as well as building many machine learning models on top of the distributed and a parallel computing environment like Spark, which is like a very super powerful combo to have. All right. So that's it on the theory part of what data science is, what are the technologies in data science. So now we'll see a very small demonstration on Hadoop, and wherein we will build a kind of an interface from R programming. So how we can like use R programming and write a program which can work in a distributed and a parallel fashion on top of the data which is stored in Hadoop. So that's what we're going to see next. So now let's see a demo of like a very popular kind of an hello world program to see how effectively a MapReduce kind of framework works in a distributed and a parallel environment, right? So we understood what Hadoop is, right? So this example that we are going to take up will get you a bit more familiarized with the framework, which we normally refer to by saying distributed and parallel computing, right? So as the name very clearly indicates, there are two parts to this entire framework. One is the data is distributed, right? I'm going to talk about that in a while. And the processes are executed in parallel, right? So both these ideas combined together is what a framework like Hadoop is. So in order for me to divide the data, there are block chunks. For instance, in Hadoop 2.0 and the later series, 128 MB is the size of each block. And once the data is put into Hadoop cluster, it's the responsibility in the framework of Hadoop cluster that divides the data into 128 MB chunks each and distribute it among all the slave machines. So as you might be knowing, Hadoop architecture has a master node which is so connected with many slaves, right? So that the data is kind of distributed among all these slaves of the size of 128 MB chunks, right? So what is the real advantage of distributing the data into smaller parts and then storing it into different nodes, right? Obviously, because we want to bring in here a mechanism which can simultaneously process each of these data blocks. So ideally, if you build a sequential program, what really happens? You have this large chunk of data, which might be, let's say, 1 GB of size. You build a program to do some sort of processing on this data. For example, let's say doing a simple word count, right? So if this 1 GB of data is actually coming from, let's say, Twitter, and you are trying to build some model for brand perception, right? In where the basic processing that you need to do is to extract or feed in your program will get this 1 GB of data and divide the comments and the feeds coming from the customer base talking about your brand into words, and then see if these words are making any sense to you. Is this a positive word or a negative word or a kind of a neutral word? So around which this entire idea of sentiment analysis really works, right? So I'm going just taking a part of that. I'm not going to talk about the sentiment analysis as such, but I'm going to talk about what we can do if we have to devise a process which will extract this each word from the given set of documents or what we call tweets, which is large in size, let's say 1 terabyte of tweets. In a traditional program, this program will sequentially run on each of the documents one by one, and then it will do the processing, which is like very time consuming and not at all efficient, right? So if I have to design this program, a very simple program which will parse the given tweet, or for that matter any document, and extract each of the words, and after it extracts, it simply counts the frequency of each of the words, the first process in any sentiment analysis algorithm, right? And in this particular process, we want to make this entire program a parallel program, not like reading the entire 1 GB data and then one by one going through each word. So how do we do this? So let's design or like try to understand a framework called MapReduce, and let's then see how this entire program can be like executed in parallel. So keep in mind there are two things that we are talking about here. One, the data is distributed and the program is going to simultaneously run on the smaller chunk of this distributed data simultaneously, or in other words in parallel, right? So here is how it works. So now imagine you have a file, right? And I'm going to just, for the sake of simplicity, keep one file. So this is my file called tweet.txt, a simple file, and it contains a lot of words. Somebody is talking about certain brands and so on. So I'm just going to take some random words here. So let's say Hadoop is fun. Fun means Hadoop, something like this. So obviously there are certain repetition of the words here. The word fun is repeating twice and the word Hadoop is also repeating twice. And then there are these words like is and means. Now you have to, like, for me, imagine here that this data is greater than 128 MB. I know this is like very small, but for the sake of explanation here, let's assume that this is greater than 128 MB and that there are going to be 3 splits of this data, right? The first split of 128 MB is only 2 words long, which is nothing but Hadoop, and it contains the word is as well. The second split of this data contains the 2 words fun, both in one, which is like good. And then the third split, which contains the word means and Hadoop. So this is the first step which happens while you want to distribute the data. So I'm just like calling this to be split, the split operation, right? So once we have split the data, the block actually goes and travels through the network to reside in one of the slave nodes, right? Which is actually decided by the master node. And like without getting into those details, because I'm like trying to come out here with a parallel program, let's only focus on this particular idea here, right? So the first process in this framework, which we are calling the MapReduce framework, is the step called mapping. So for a simple process like this, what is this mapping? As I said, it's simple, right? So the idea is in this mapping step, for each of the words which is contained in the block chunk, I'm simply going to append a 1, which in a way means I'm going to create something called a key and a value pair. So the key here is the word, and the value which I am associating with this word here in this step is 1, which means I am counting this word once, right? So similarly, the process would be repeated here as well. So there are once again 2 word fun. I'm appending a value 1 here with it, and the fun is actually coming once more. So I'm going to append one more 1 here, right? And in the final sort of block, the same process comes once again. And here we have 2 words. First the means, which is like given a value or count 1, and then comes the word Hadoop. Right. After we are done with this process, now imagine that what's really going to happen. Because we know that each of these blocks are separate, and there would be like 3 copies of the mapper program which is actually running on each of these block chunks simultaneously. So actually when I wrote this 1 like appending a value with each of the key there, for each of these blocks the program was parallelly running, right? That's the sort of power we are able to get because of breaking the data into smaller parts. So now my one program is not actually running on one large file of 1 GB or 1 terabyte, but rather on a small block of data, which is obviously fast, and because this parallelism is also achieved, the kind of speed is even more like even better. Okay, but now comes the challenge, because each of these blocks doesn't know about each other. Some master is controlling this split. So how do I now get my final results? The final results that I would expect from this program is to give me something like this. Hadoop is actually appearing twice. The word fun is appearing again twice. The word is appearing once, and the word means appear once. So this is the final output I am looking for. But at this particular step, I am kind of bit stuck, right? How do I now combine the outputs? So at this particular moment, we have to kind of merge everything together, right? Or what we call the operation as shuffle. So what this shuffle does, and the name shuffle is because over the network, these block has to be transferred to one single position or place where I can like simply take the word and start to append something with it. So what is that append? I'm going to like write it down here. So let's create one block. It can be like multiple blocks as well in the shuffling part, but for the simplicity's sake, I'm just going to keep like only one block. Here I have this word Hadoop and the values, 2 values that are going to come up with this. And now like imagine how this is happening. There is this key 1 and a list of values, right? Because we know that the key uniquely identifies this word, we are able to identify when the sort of over the network the blocks are transferred after this result, which is like the key value pair. I am able to identify the particular word and then like concatenate the list of ones along the key. Same is the case with the word fun as well, because the key is going to be same. I am going to collect all the ones with it. And then comes the word means, which has only one, and then comes the word is, which once again has 1, right? So once I get this data right, like after the shuffle, which had the network transfer as well of the blocks, or rather the key value pair, not the blocks, I would simply go for the final step in this framework called reduce, because now I have the global view of the entire data set, which contains now every single word in a very simple straightforward one operation, which is simply the sum I'm going to calculate or iterate through the list and append its count. Fun appearing twice, is appearing once, and the word means also appearing once. Quite a simple approach, right? So there are like these two key steps, which is the mapping of every word to the integer 1, which is appended to it as a count. And then over the network, a shuffling happens where you create a list of the values for every key. Once this list is created, the final operation that you take up in the program, which we call reduce, is simply to take list of values and sum it up, and you have the final results. Okay. Though this example sounds very easy for the explanation's sake, but there can be processes which is quite more complicated than this. And be very cautious of the fact not every single operation is actually programmable in a parallel fashion. Right. For instance, if I want to do the same sort of like an analysis, but the operation that I want to do is not sum, but rather averages, right? So if you are given 1 million numeric values and the operation that you want to do in parallel is to compute the average. So average as an operation is actually not possible. Like if you do the blocks like this and calculate the average of, let's say, first 1,000 numbers on this block and then the next 1,000 numbers on this block and so on, and then finally get everything together to again calculate an average, mathematically this is wrong, right? So in these sort of operations, writing a parallel program is not possible. So with this fact, the idea is pretty simple. The program name MapReduce actually came from this idea that the data can be distributed and divided into smaller chunks and the processes can run in parallel. All right. So with this framework in mind, let's see a demo in one of the virtual machines of Edureka where we have our Hadoop setup as well as our programming, our studio, and everything is like running good here. So for instance, if I want to very quickly check the health of my distributed file system, the Hadoop distributed file system, or in short what we know as a DFS. So keep in mind, in the demonstration here I'm using a single node system, so the master and the slave both are actually this machine, which in other words means this is actually a pseudo cluster with only one master, like one machine acting both as master and the slave. So in this architecture, I can like very quickly go through and see what all is like the information of my cluster, and the most important place where I can go and see the file system of Hadoop. Right. So this is how the file system of Hadoop looks like. So there are like so many directories that I've created in the cluster here. And remember, all of these are going to be distributed across the slaves. And as you can see, the block size, this is what I was actually telling you. When Hadoop divides the data into smaller parts, that actually is 128 MB each of the block. And you can also go and look at inside the particular file that what it contains. Right. An alternative to look at my file system is to go in the terminal. So those of you are like good in using command line interfaces. From terminal also you can look at all these files that are existing in your HDFS and also do certain file operations. Right. So before we can actually run a MapReduce program on the data, we need to actually create some data and then put that into Hadoop. Right. Then only we can like proceed with the process of running the algorithm. So let's see how we can do that. But before we go into creating a file and then putting it into Hadoop, let's very quickly see what all is the file that is present there in the Hadoop file system. So you have to like specify that I want to look at all the files in the root directory of my Hadoop file system. So the command is like something like this: Hadoop file system -ls /. So you see whatever we were like looking at few moments before in the browser, it's actually listed out here as separate folders, and I can go to any one folder particularly and see if the file is present there or not. Right. I'm going to open a parallel window to this to create some file which I can then put into this file system. So let's create using some of the editor here. Let's use the nano editor and let's write something to this file. Hadoop is fun. Let's like you make sure the cases are taken care of, and the periods are also like taken as a character. So I'm like making it a bit more cleaner. Fun means the same example, and the case should also be important, otherwise it won't count. And I can also like put some new line character here and enter something more, maybe. Let's say welcome to Edureka demo session, right? Edureka offers data science courses, like something, whichever you want. So now let's save this and very quickly see if we can. Yes, we want to save the file with some name. Let's give this file a name, Hadoop demo.txt. Okay, so let's see if this file is actually created in the current working directory. Oh yeah, so we can see the content there, the one which we created. So let's come back here and see if we can put this file into the root directory of Hadoop file system, right? So before that, let's look at the present working directory. Okay, so this directory is called home and Edureka. So let's use that here. So we are going to use the Hadoop command for file system copy pastes, and the command that I'm going to use is put, right? So I'm going to put this file that we just created, home Edureka, and the file which we named Hadoop_demo. Right, and where do you want to put this file in the Hadoop file system? Let's put this in the root directory itself so that it's easy to like call this. All right, let's hit enter and see if this is successful. All right, that was quick. Let's look at very quickly once again if the file is present there, Hadoop file system, and let's say ls. Do you see the demo.txt file? Yes, it seems like the file is present there. Just to double check if this is true in our browser view as well, let's go to the root directory here and see if there is any file like Hadoop demo. Yes, it seems like it is present. Let's click on this, and the content is absolutely what we wrote, right, in the file that we created. So all good. So we have now created a file and then put this into a HDFS cluster. So now we are all ready to run our MapReduce program. Okay, so keep this in mind that whenever you are executing a particular parallel program on any such file system like Hadoop's or Spark's, then there is a native language which actually is built with Hadoop and Spark as well. So for instance, Hadoop's native language is Java, and Spark's native language is something that we call Scala, right? So these native languages are the most robust languages to be working with, but having said that, the expertise around programming has evolved over a period of time. People starting with like Fortran kind of languages to Pascal kind of languages to C, C++, Java, and it has like evolved now into so many in number. So it's very hard for somebody to be like learning every new language which is like coming with the new technologies now and then. So that's why most of these technologies, to get a better adaptation, also build such kind of interfaces with the other programming languages. So using the other programming languages and the syntaxes available there, we can still be able to execute the program on a distributed scale. So that's what we are trying to do here. In the beginning, Hadoop didn't have such kind of interfaces. It was only working with the Java one, but later on, as the time evolved and as the kind of ask and requirements started to increase, people did come out with such interfaces. And the way Hadoop really supports this is actually in technical terms termed as Hadoop streaming, right? And there is this jar file which comes with the Hadoop installation itself, which you need to use for you to be able to execute the R program on the data which is sitting on top of Hadoop distributed file system, which is HDFS. So here in this case, there are two environment variables which I need to set. So both these two settings needs to be given in the beginning of your program, so that from this console of R, you can be very easily like you can identify and tell our programming here or our engine here that I'm going to connect to Hadoop and get my data from there, and I want to execute this program on Hadoop rather than doing it on any local file which I've kept in my system. Right. So the first is your location or your system environment variable, which says Hadoop is installed in this particular location inside your virtual machine. And then the second, as I said, is to build this interface between R and Hadoop. So this is done by this particular jar file called Hadoop streaming. Right. So once we have like set up this environment variables, let me run this. There are also certain packages which will help us to now execute things on Hadoop, right? It is not possible that you can simply start writing your MapReduce logic and that it will automatically connect to Hadoop. It doesn't like work that way. So as we were doing things in our terminal, right, we were typing some commands, which was possible because we have installed Hadoop in this cluster. Similar way, for R to know that I'm going to work on data in our HDFS and I'm going to run a MapReduce program, there are these packages which is being built. So the two important packages in those terms is one which we call RMR2 and the other which we call RHDFS. Right? Both of these will interface with the Hadoop data, and then one is for accessing the file system, which is this RHDFS, and the other which is for the MapReduce program to be executed on that data. So both of these packages are going to help us. So you need to install that using this command install.packages and make sure that you are connected to internet, otherwise this will fail. So I've already done this installation, so I'm going to run it, going to load the library directly. Okay, and the first step after I load the library is to initiate the connection from this R session to the HDFS. So it will take some time there. Okay, so it seems like there is this warning message, no worries around that. So now you can imagine that every single command that we were firing through terminal, because we have now built this interface from R to HDFS, you can do that in this place itself without going to terminal or to that particular browser interface that I showed you. So for instance, the same command that I was using, the Hadoop fsls, right? If I want to execute that here, this is how the function looks like, and all the files will be listed. I'm not going to create a directory, but there are many other functions as well, which is typically supported by the Hadoop file system. You can run that from R itself. So let's run this and see if it gives the same result. You can see that this is the same set of files and folders that we earlier saw using the terminal and the browser interface. And this is our file which we are interested in. Okay, so let's now use this. So there are some more commands by which I can delete some files, and the put command that I used in the terminal, I can also use the put command from here. The syntax is slightly changes, but quite easier than the command in the terminal, and works the same. All right, so let's now get into the main part, the one which this program is actually built for, the map and the reduce program. So as I said, both these operations are quite different in nature, right? So we don't really have to write that shuffle function that I described, right? That is taken care by the inbuilt function provided by the RMR package. All we need to do is like read the data and parse it. That's this first kind of function that I'm going to create. So you remember that every key value pair first needs to be generated. So this particular step will help us doing that. So the function which I'm going to define, called map_func function, will take a particular key and every line of the given file, and you will see how I'm going to use this function a bit later on. But as of now, let's see the definition, how I'm doing that. After I get every line, so there are like, let's say k lines in my given file, and each line is first presented to this function called strsplit, which splits the content of the line by white spaces. So if we have two words separated by one or more spaces, it will split the content and put it like a list of words. So once you run this particular string split function on each line of your file, you will get the words separately as a list, right? And then you'll apply something called an unlist function, which is just to make sure that I'm able to pass this to a mapper function, right? So that's the kind of a requirement there. And with each of the extracted word, I'm very simply going to append a 1 to it, which is what we actually did in our mapper function, if you remember, right? We extracted first the block of data and each token from it. By token, I mean each word, and then you appended a 1 with each of the word, right? So that's what your mapper function looks like. And the reducer function is even more simpler. You get these words and the counts, which is coming with the count here is nothing but the one which is coming from the mapper function. And all you need to do is generate the word along with the summation of all the list of ones which is being given to you by the mapper function, right? In separate parts, these two functions looks good with the logic that we like just understood in the explanation. But how do these two functions really coordinate with each other? And that's where we have this function called MapReduce in the package RMR2. So if you want to read more about this particular package, you can go to the help documentation of R, right? And it says defines and executes a MapReduce job. That is what we wanted. And this is like achieved using what we like know as Hadoop streaming that we just saw. So now this main function is what is going to bring in this kind of an interaction between the mapper and the reducer function. So it says there is this input. I'm going to describe this input in a while. Actually, this is an input of input which says that this is where my file exists in the Hadoop file system. The output means the location to which I want to write my results back, right? We are going to define this somewhere in the bottom. And the input format is a text. The mapper function name is map_func. The reduce function name is reduce_func. So these are the arguments to this MapReduce program. Quite simple, right? Okay, now let me like create these functions one by one, or I can like select all of it and say run. So remember, we have just defined the function, but we have not executed it so far, right? So everything is good in place. I think I need to just set my correct input directories and things should be like good to go. So let me give the base directory here. So the base directory is actually the root. So there is no directory that we separately created. And inside this base directory, we know that our file name is Hadoop_demo. And where do I want to store my results? Let me now create a folder rather. Instead of putting that into the base directory, I'm going to create a folder which is named wc_out_r. So this is where I expect to find the result of this function or result of this entire program. Let me define all of these one by one now. Here we go. And now we are ready to give in these inputs to the function we created like few lines before, like this one. We created this function called word count, which uses the function MapReduce coming from the package RMR2. So now let's run this and this should start hitting HDFS. Okay, let's see. Let's create this as well, and let's make sure the init is working, and then let's go. The base is ready. Hadoop_demo.txt in the base directory is my input, and this is where I'm going to do the output. The word count is ready, and let's run this. Right, so if you see here, the output of this program is like now should be present in the HDFS. So the job has completed, and as you could see here in the progress, initially the mapper program started with some progress being shown here, 0%, and the reduce was at 0% there. And when the entire mapper function has completed, that means every single data block has been processed and key and a value pair was generated, the reduce program starts. Right, till then the reduce program was not doing anything, and then the only operation that happens in the reduce program is to take the sum. That's it. Right, once the job was completed, you can see the final end result as done. So if we now look back, like very quickly showing you, the directory should be created, and here you go. Let's look at the part file. All right, so this seems to be a problem. The output is actually present with a success message, but it seems like we cannot read this, right? Because there should be some sort of encoding which our programming would have done while it is writing the data back into HDFS. So in order for that to work, instead of looking at the HDFS data directly from the browser interface, we are going to read the file here itself by using this function called from.dfs. And if you pass the folder location in which you have written the results, right, you have stored the output of this program in the folder called wc_out_r, where this file part 00 something is created. So if you run this function called from.dfs, it will actually fetch the result of your program from the DFS, and we can then process it as simply as like a data frame. So let me like read that file using this function, because now this function will know the sort of the encoding that the our function, which is the MapReduce one, has done. So when it is reading, it will decode it first and then read the results. So right now the result is in form of a list, as you can see on the right hand side, right? So instead of that, I would like to read that as a data frame, which we are very comfortable in using. All right, let's give some name to the header of this data frame that we newly created, and let's print it now. Right, you can see here the result seems to be right. We had the Hadoop twice, we had the word fun twice, we also had the word Edureka twice. Seems like it worked, and it was quite fast, though we were not able to see that great speed because the data that we used in order to keep the demonstration time in intact, even with the thing here, the framework kind of worked very good. like by distribution of the blocks and then getting the parallel program run on it. Just the last step here, if you just want to look at the output in a sorted form, you can like run this command on order and order the basis of the variable count and in decreasing order, right? So once again, with the MapReduce framework, even some of the most complicated processes which can be broken down into parts and a parallel program can be designed for it, it's quite easy to build a really fast processing framework. And the moment you are able to do this fast processing, the next coming steps are going to be pretty fast as well, right? Because this fundamental one step could be an important input to the other processes that you might be wanting to do with this data. For instance, here, if I want to build a sentiment analysis, the first step is to break the data into smaller kind of chunks or tokens that we call and start counting the frequency of the words. So if I'm able to run that particular process quite quickly, 1 terabyte of data might be reduced simply to some set of 1 GB of data which will only contain the word, but the rest of the repetition of the words and all that kind of will be completely taken out there, or it is not present there. So the data size as such is reduced. At the same time, you're able to run a program in parallel on a distributed data set. All right, that's it from me on this side. Hope you enjoyed the demo. Thanks. Bye-bye.